about multiple random variables, or the case where we have two random variables. We had listed out some properties of the joint distribution function, and we had said that we had listed out certain properties of the joint distribution function, and we had I'll just skip those properties and just write a statement that, okay, the pen is acting again. Hold on. If the oh yes, so we had last thing that we had covered was this conditional distribution. Fine, and it said that if y remains by conditioning on x, then x and y independent. So they are called independent random variables for any function g write it like this. That equals x, y. Expectation of equals minus infinity g xy fine. If has the correlation between we define the covariance of X. Okay, so we haven't talked about complex random variables yet, so no complex conjugation, and the joint characteristic function of psi expectation equals now we define the correlation between X and Y as Rxy equals expectation of xy. The covariance of X and Y as sigma xy equals expectation of x minus expectation times y minus expectation expectation of xy minus expectation of x expectation of y. This you can show. This I leave for homework. Homework means the guy who does the transcription assignment at least has to do it. Fine. And the correlation coefficient between y fine. Now for some slightly counterintuitive definitions. Two random variables x and y called orthogonal. So Any guesses or anyone remembers this? Orthogonality, anyone remembers?
Correlation is 0.
Yes, expectation of xy is 0. And they are called uncorrelated if x minus y. This beast is 0. Fine? Or as we have orthogonality implies decorrelation only if either x. This I believe is fairly obvious. And two words are called independent when the multiplication of x by x of x. Fine. In general, independence implies decorrelation, but the converse is independence implies decorrelation, but the converse is not true. Fine. So,
Sir,
yeah.
sir, what
Yes.
does decorrelation mean?
Decorrelation means that, so yes, decorrelation between that x and y are decorrelation or uncorrelatedness, whatever you want to say. Uncorrelatedness is slightly longer, decorrelation is slightly shorter. So since I'm lazy, I use decorrelation. Fine.
Yes, sir.
Great. So now consider the case where the random variable z, instead of being defined as or from uh, from So this I believe you wouldn't have covered in your probability. Did you cover complex random variables in that course? Anyone remembers? Did you cover complex random variables in the probability and random processes course? Okay, so can in this case define z equal to x plus j prime where x and y are both real valued random variables and hence z represents mapping from the sample space to the complex. Fine. So instead of mapping from the sample space to the real line, we are now mapping from the sample space. So I'll just write omega slightly nicely. Orange is okay. Fine. So now the question that you might ask is, we just talked about two random variables. How are these different from a complex? Right, so just always be careful that I'm not selling you snake oil. So how are these different from a single random from a random variable? So the thing is that I can represent complex right, and I can represent it like this, where r equals One thing is, fine. This is uppercase theta, that is lowercase theta. Since we represent random variables using uppercase theta, we can get this. Fine. So this. Now, the next question that you would want to ask is, what about so, or rather, so what is the most fundamental problem in defining the CDF of Z? Oh, sorry, not this Z. This is the set of integers. Capital Z. Yeah. What is the most fundamental problem in defining the CDF of Z?
We can't compare complex numbers.
We cannot compare complex numbers. Yes, Bala. You spoke too early. I was going to announce 2 bonus marks for this, but you spoke before that. Anyway, you already have bonus marks. So I'll put some bonus marks for you as well. Great, no problem. Yeah, anyway. So another 2 bonus marks. So yes, as Bala said, we cannot compare 2 complex numbers. And therefore, the definition of the CDF is tricky, but we use the element wise CDF. So when we talk about the CDF, we'll always talk about the element wise CDF, that is Fz of Z, or we play a slight trick here, equals xy x or probability that x is less than, I'll write it like this, real of Z fine, or equivalently f z theta or f r theta, sorry. Magnitude of Z. Fine. So now the question is, how do we define this FR theta? Another question is, if right, so this I'll go back to the fundamental definition of the CDF and write R theta probability R less than and theta less than equal to capital theta theta or probability the pairs xy such that root over x square plus y square r and tan inverse y by x less than equal to theta. Note that x, y right. Is this right, Pala?
Yes.
Yeah. So now similar to the case where have a random variable whose PDF is known and we want to obtain the PDF where has a countable number of solutions for all y. Fine. We have the case Here we know the PDF of or we know the joint of X and Y and of then there's a direct formula like the previous case. Sorry, my bad. Then so such that these two have countable number of solutions for all W. This is the condition, and is summation I in A 1 over Ji fxy xi yi A is the set of all physical solutions of with xi being the ith solution pair. Or I'll write it like this looks better this way. With or for all xi yi this pair, these pairs elements of the fine. Oops. Ji is by del x del w by del y x equals xi, x equals xi, y equals yi, y equals yi, and this. So this is the determinant of this beast. So anyone remembers what this beast is called?
Jacobian.
Yeah.
Yes, Jacobian. This is the Jacobian of gxy. This thing is the, so that's why we use the symbol J. Jacobian of fine. Also, since z equals x plus jy, expectation of z equals expectation of x plus j times expectation of y. Fine. This is fine. Guys, looks fine. Yash, Bala, Gandhi.
Yes, sir.
Yes, sir.
Yeah, so if we go back to the other courses, what does the mean square value represent in general? When we talk about the mean squared value of anything, what do you associate with the mean squared value of any quantity? For example, current. What do you associate with the mean squared value of that current?
Some sort of average, but without considering sign.
Some sort of average. What?
Without considering sign.
Yeah. So, Bala, let's refine your answer. So, what sort of average? What does the means average of what generally? When I say the RMS value of current, RMS value is quite familiar. You guys are doing that since last 12th. So when I say the RMS value of current, I say that it's the root mean squared value, 1, fine. We are okay with that. But when I remove the root, what does, suppose I am talking about the root mean square value of current passed through a 1 ohm resistance. What will that represent then?
Same power.
Power, yes. So generally, we are used to these mean squared values representing power, or that is the way we think of it. So power cannot be complex. One. So mean squared values, I'll write this down. We are used to representing mean squared values as powers, and power cannot be not talking about reactive power electrical people. It cannot be imaginary, right? And obviously it cannot be complex. So have to redefine our notion of mean squaredness when encountering complex we have to redefine our notion of mean squaredness when we are encountering complex random variables, and for that let us look at the expectation of z complex conjugate. How do we write it generally? Mod of z square, right? This equals expectation of x plus jy x minus j. Fine. Equals plus j expectation. Fine. This is more intuitively more satisfying that this will always be non-negative. This can never be. So it's zero when only x and y are zero, and it looks like the sum of the mean squared value of x and y. So oh, yes, this is intuitively more satisfying. Do you agree, Nikita? Do you agree on that? Yash, would you agree that this is intuitively more satisfying?
Yes, sir.
Yes. So with this intuition satisfied, is someone sending a chat message? No. Why is my Teams account blinking? Oh, other group. Yeah. So yes. In general, for two complex RVs Z1 and Z2 define the and covariance this beast. Now it is time to define the complex Gaussian random variables. Or okay, so this is what I will do. I'll write down the yeah.
Sir, here we are defining like in normal case also E of xy as a correlation, right? But
E
in
of
the means xy, like here it is z2 star.
Z conjugate, yes. So
So
E of xy will become, if x and y are complex, it
means
will become,
this is shown as means correlation, right?
this is the
But
correlation.
in the
Yes.
other place we are defining correlation coefficient as covariance by
Correlation and
product of
covariance, correlation and correlation coefficient are two different things. Sorry, Raj. So see, all of this notation developed more than 100 years ago. So more than 100 years ago, people somehow developed a confusing notation that correlation. So that's why I discussed that in detail, that correlation is something totally different from correlation coefficient and covariance, and uncorrelatedness arises from correlation. Sorry, uncorrelatedness arises from covariance.
Sir, can you repeat one?
So, okay, if you look here, earlier what we had done earlier, I'll just scroll up. See, this is correlation. This is covariance. Maybe I'll change the color of the pen. So this is correlation. This is eraser isn't working. Wow. This is covariance, and this is the correlation. Three different things. So these you have to, someone or the people who named these unintentionally named these confusingly. So you have to be very careful while referring to one of these.
Sir, when we are saying something is uncorrelated, we are actually
When
using
we are
it
saying
in sense some
that covariance is zero.
covariance means this coefficient is 0.
Covariance is zero or correlation coefficient is zero, whatever you think of it. When we are saying orthogonal, then we are saying the correlation is zero.
Oh.
So you have to be very careful while using these terms.
And so for orthogonally correlation, we
Orthogonality.
have
Correlation is 0 for orthogonality. Covariance is 0 for
0 for uncorrelation.
uncorrelatedness or decorrelation, whatever you want to use. Fine.
Yes, sir.
So complex Gaussian case. So yes, so it's 53 already. So I won't start the complex Gaussian random variable now. Maybe we'll start this on Monday. Start and finish this on Monday. So, and you guys have any questions, you can ask them. We have another 2 scheduled minutes of class left. Any other questions? Open session, anything, not just what I have taught today. Midsems and all, because midsems are approaching. Okay, great. So what should I do? Okay, then I'll continue with the complex Gaussian.
Yes, sir.
Yeah, yes, tell me.
Can you tell something about how the midterms will be conducted this time?
There's a big question mark. I will do what the. Okay, let me stop recording. It's better to not put these things on record.